Hey class, 5.3a. Today we're going to look at how to analyze the graph, so different features of a polynomial, and we're actually going to write equations of cubics in this as well. So first, a little bit of vocabulary. We're going to be identifying the local maximum and local minimums. Now, the maximums they're both y values. And the local maximums are the y values at the top of like the curves. And the local minimums are the y values at the bottom of the curve. So for example, let's see if I can draw like a little curve here. So this is a cubic function. It's got two turns. Well, let's actually do one with maybe a little bit more turns. Let's make a quartic function so you can see a better example. The low points here, this would be a minimum, and then this would be a minimum as well. So the two y values there, and then up here would be a maximum. And so this would be the maximum, but it's the highest value, but it's also a local maximum too because it's the only one. And then these are minimum values. We call them local minimums. Okay, so here it's defined again for you. The y coordinate of the turning point is the local maximum of the function. If the point is higher than all the nearby points, the y coordinate of a turning point is a local minimum. The local minimum is the point is lower than all nearby points. So let's just practice finding those. This is just estimating the x-intercepts and local maximums or minimums from the graph, and then identifying the lowest degree of the polynomial. So I'm going to start with the maximum points. Those are going to be at the top of the hills, and it's the y values. So the local maximums are going to be y equals, I got y equals 3 for the one on the left, and then I don't know, like 1.6 for that one. And then local minimums, I'm gonna do the lowest points, so at the bottom of the curves, and the y values, so maybe negative 1.6 and then negative 3. So this one's kind of symmetrical in that way. And then x-intercepts. X-intercepts are where it crosses the x-axis. So we have 1, 2, 3, 4, 5 x-intercepts. And x-intercepts can be written as x equals or typically as an ordered pair because it's a xy coordinate. So the first x-intercept looks like it's about negative 2.1 and then it'd be 0. The next x-intercept looks like it's at about negative 1.1 and then 0. So that's these first two right here. And then the origin is a x-intercept, so 0, 0. And then over here we got like positive 1.10 and then positive 2.10. So those are my x-intercepts. It has 1, 2, 3, 4 turning points. And notice that it has 2 maximum and 2 minimum points, so 4 of those, which means it has 4 turning points because the maximum and minimum occur at where the hills and valleys are. And the number of turning points has to be 1 less than the lowest degree, which means that this could be a degree of 5. Would be the lowest degree. It could be a degree of 7 or 9. I do know that it's going to be odd based on the end behavior because the left side goes down and the right side goes up to infinity. So it is a positive odd function. It increases from left to right. So the lowest possible degree would be 5 because it has less than or equal to 4 turns. Remember, the number of turns is 1 less than the degree. Okay, over here, max, min, and x-intercepts. So the maximum is going to be at the top of the hill, which is right here. And this graph is counting by 2's, which means that maximum is at y equals 4. The minimum is the bottom of the hills. There's only one here. So that looks like it's about 1.9 for a minimum. The x-intercept is where it crosses the x-axis. There's only one, and it's at -4, 0. It has 2 turns, so 1, 2. It has 1 max and 1 min, so 2 turns, which means that the lowest degree would be 3, 1 more than the number of turns. It could be a degree of 5 again, or a degree of 7. I know it's odd based off of the end behavior. So if we plug this function into our graphing calculator, to save some time, I have a picture of what it would look like here. And then just estimating those zeros. So I'm going to also show you Desmos quick, actually. So y equals, Desmos is really nice, x to the 3rd power, whoops, minus 5x squared plus 4x plus 3. So Desmos is really nice because it actually identifies all of the key points for you. If you tap on the graph, you can identify, here's my x-intercepts. So if I want to write those down first, x-intercepts, negative 0.4610, 1.7610, and 3.70. It's likely that those are irrational values, and Desmos is rounding. And then if you tap again, you can get the maximum and the minimum points, so the high and the low values. Remember that the max and min are just the y values. So at the top there we have 3.879, and then the local minimum would be negative 3.065. We would use all of the maximum points if there's more than one, but this only has one top of the hill and one bottom. And then it also gives me the y-intercept here. Not that I asked for it, but the y-intercept is at 0.3, so that's another important point to identify if possible. So Desmos is really handy. It already gives me all of the key points if I tap on the graph. All right, just a couple more critical thinking questions. If you have a 4th degree polynomial and are given one imaginary root, what is the maximum number of real roots that you can have? Well, if my polynomial is 4th degree, that'd be like x to the 4th. That means that it would have 4 roots or 4 solutions. That comes from the fundamental theorem of algebra. So if we remember from the lesson earlier this week that imaginary roots always come in pairs. Let's say that you had one imaginary root given like 5i. Well, then you know that you have to have both plus and minus negative, plus and minus 5i. They always come in pairs. So that means that if you have 4 roots and one is imaginary, you actually have 2 imaginary roots, which means that there's 2 real roots because the total number of roots was 4. So the max number of real roots it could have would be 4. Sketch a graph of a polynomial function that has 3 roots. One of them is real and has this end behavior. So as x goes to infinity means as you go to the right, the function goes to negative infinity means that the function goes down. And as x goes to negative infinity, so as you go to the left, the function goes to positive infinity, it goes up. So on the right side, it goes up over here. So we want to go up on the right. And then on the left, we want to go up as well. Oh, wait. Sorry. I messed that up. As you go to the right, negative infinity would be down, not up. Okay, as you go to the right, you go down. As you go to the left, you go up. This function has 3 roots, which means it's an x to the 3rd power. So it looks something like this usually, or this, depending on the end behavior. It has 1 real root, which means that it has 1 x-intercept. A real root equals an x-intercept. So one x-intercept, and I couldn't quite make it back to my arrow there, but so one x-intercept, down on the right, up on the left, look like that. 3 roots means that it has to have less than or equal to 2 turns because it is an x to the 3rd power, so 1 less than the degree. Sketch the graph of the polynomial function that has 2 roots, none of them are real. Well, 2 roots is an x squared, which means it has to have less than or equal to 1 turn. None of them are real means no x-intercepts. As x goes to infinity, so as you go to the right, the function goes to infinity, so up. As you go to negative infinity, so as you go to the left, whoops, can I spell left? The function goes to positive infinity, so up. So up on both sides, and it has no x-intercepts, and it can only have 1 turn. So like that. Okay, next we're going to write equation of a cubic function. So cubic functions have 3 roots. And so similar to what we did in the last section, you have your f of x equals a, and then it's x minus the root times x minus the root, x minus the root. Now, in a polynomial function, that could continue for as many roots as you have. Like if it was a 5th, you'd have 5 of them. Cubics have degree of 3, so you have 3 roots. The roots are the x-intercepts, so identify them first. So we have 1, 2, negative 3, x-intercept of negative 1, and positive 3. So the first thing I'm going to do is plug that in. So f of x equals a, x minus negative 3 will be x plus 3, x minus negative 1 will be x plus 1, and then x minus 3. So if I was to solve this, I'd get negative 3, negative 1, and 3 for my answers. So those are my roots. Now, it might be worth noting, I'm going to change this f of x. Remember that f of x is the same thing as y equals, and that's going to help you in the next step. So the last thing you need to do is solve for a. To get the a value, you will need to choose an xy point, not an x-intercept, some other point on the graph, like this one that was given to me, negative 2, 1. And this is an xy point. I'm going to plug x and y in and solve for a. This one increases from left to right, so your a value should be positive here. So I'm going to plug 1 in for y, so 1 equals a, and then plug in negative 2 for x, so everywhere I have an x, and then multiply. So negative 2 plus 3, negative 2 plus 1, negative 2 minus 3. So 1 equals a times, this would be 1, this would be negative 1, and then negative 5. So 1 equals a, 1 times negative 1 is negative 1, times negative 5 is 5. Then to get a by itself, I have to divide by 5, so a would equal 1/5. So to get my final answer, I'm going to take that 1/5 and substitute it back up in here for this a, and then that's your answer. So my final answer would be 1/5, and then x plus 3, x plus 1, x minus 3. All right, let's do that one more time. So first, identify your roots. So I have negative 1, a positive 2, and a positive 4. So first, x minus negative 1 will be x plus 1, then x minus 2, and then x minus 4. So remember, it's always x minus the root. X minus p, x minus q, x minus r, I think it is originally. Anyways, then choose an xy point on the cubic that is not one of the x-intercepts. So like this one, you can use the y-intercept. This is the point 0, 1, 2, 3, 4. So if you choose 0, 4, try to choose a point that's given to you, because even though I could choose this 1, 3, I don't know for sure if that's exactly where it crosses. It could be a different point, like close to that. So try to pick one that's given. So X and Y. Plug in the 4 for the Y, so 4 equals A. Plug in the 0 for the X. 0 plus 1, 0 minus 2, and 0 minus 4. Then simplify, do the addition and subtraction in the parentheses. So 1, negative 2, negative 4. Then multiply these three together. 1 times negative 2 is negative 2. Negative 2 times negative 4 is 8. Then finish solving for A by dividing both sides by 8. Now 4 over 8 does reduce to 1/2. So A equals 1/2. Then take that A equals 1/2 and plug it back into here for A. So final answer would be Y equals 1/2, X plus 1, X minus 2, and X minus 4.